This is a video to show you how to use the manipulative, which graphically shows you how to derive the equation to figure out the sum of a geometric series. Um, Basically, think back to our exploration where we saw that a geometric sequence can be represented as a kind of a curve like you see here. So a geometric sequence, remember, it starts with a number and then every following number is multiplied by the same number. And so this one you're seeing here is the geometric sequence 1, 2, 4, 8, 16, 32, 64, 128. And you can see the blue one, it goes up to 128. You can see that the 8th bar in the blue one is marked 8, 128. And the red one has 9 bars and it goes up to 9, 256. So you can see that these are the same sequence. It's just that one goes to the 9th term and the blue one only goes to the 8th term. So you can see that the last term for the red one is twice as high as the last term for the blue one. Okay, and so we are going to use these two images to show graphically how the derivation of the geometric sum formula works. And the way it works is there's a trick, which is that a geometric sum is recursive, which means if you take a geometric sum and you multiply it times the common ratio, which is that special number which creates the next bar from the previous bar, if you multiply it by any multiple of that special number, you basically are taking that geometric sequence and you are making it into a later version of itself. Now that might not make much sense, but for example, we have 8 bars here and they go from 1 through 128. Now what if I took each one of these bars and multiplied it by times the common ratio, which is 2? I'm going to press my mouse button and that's going to automatically do that. So when I press the mouse button, it multiplies every single one of these bars by 2, which is the common ratio. Now you can see that if I push that, it basically takes the first bar, which was 1, and now it makes it 2. It takes the last bar, which was 128, and makes it 256. Okay? So we're going to use this special property of geometric sequences to derive the formula for the sum. And remember that a sequence can be represented as bars like this. If you represent a sequence as bars like this, then you can basically represent the sum as the area of these shapes. So for example, when I'm trying to find the sum of this blue sequence, it's basically the area of all these bars. And when I'm trying to find the sum of the red sequence, it's basically the area of all these red bars. So I'm going to use the fact that multiplying by this blue one by the common ratio, which is 2, I can make it into a later version of itself to figure out what the formula for the geometric sum is. So if you look to the right, there are some drawings here, and it basically shows that the red bars kind of make a curved shape, and the width of them is 9, as you can see, and the height is the 9th term, which is 256. And the blue curve is 8 wide, and it has a height of 128. Okay, so we can see that in the notes here on the right. Now I can cover the red region with this blue region in 2 ways. One is I can cover it, if I scoot it all the way to the left, I can cover the red region's 8 left bars, and then I only have a red bar left over on the right. So if you look at the notes on the right, you can see here that there is, if I do that, then the left region, which I can call that S of 8, which is like the area that's 8 wide, it covers the 8 left bars. And then left over, behind it, I have S9, which is the red area, which is 9 wide. But what is basically showing through is U9, which is the last ninth term of the red geometric sequence. So if I take the area S8 and I add U9, which is the last of the ninth term, that gives me the area of S9, which is the red region's area. Okay, so S9 is equal to S8, which is the blue region, plus this leftover red region, which is the ninth bar. It's called U9. Okay, now the other way I can cover the red region with the blue region is if I scoot the red-blue region all the way to the right and I multiply it times the common ratio, which is 2, you can see that the 128 immediately shoots up to 256. And I am now covering the red region with the blue region. Almost, but not quite. You can't really see it, but like the first, you can see that the first term, I'm putting it over the 2, and when I multiply it times the combination of 2, that 1 becomes a 2, and it covers the 2 perfectly. But I'm no longer covering the leftmost term, which is the first term. So if you look here, the blue shape is covering the right 8 columns, and the first column is not covered, and that column is actually U1, which is the first term in both sequences. And so I'm going to use that trick to take the total region here, which is the red S9 region, and I'm going to break that into two components. One is the U1, which is the first term, and then I'm going to add R times the original blue region. So like the original blue region does not cover the red region without pressing the mouse, but when I press the mouse, which is multiplying by the common ratio, then it covers it. Okay, so to make the blue region taller, I need to multiply by R, which is the common ratio. So if I have U1 plus R times the S8, then that also covers perfectly the S9 red region. So I'm covering S9 in two different ways. So I start out with an equation that's S9 equals S9, which is obviously true. And then I'm covering it in two different ways. One is I put the blue region on the left, and then the ninth term is left over. And the other way I cover it is I put it on the right, and I multiply it by times the common ratio, and then this little piece on the left is left over. Okay, so I'm covering it in two different ways. And then now it's just algebra. I'm going to take U9, and the ninth term is actually equal to the first term times R times R times R times R, right? Because the first term is 1, and then the second term is the first term times R, and the third term is the first term times R times R, and the ninth term is equal to the first term times R 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 times R. It's equal to U1 times R to the 8th. Okay, so that's what I have here. I changed U9 into U1 R to the 8th. Okay, and now it's just algebra. So for example, I'm going to put the S8 terms together on the right. So I'm going to have R S8. I'm going to subtract S8 from both sides. Okay, then I subtract U1 from both sides, and I end up with U1 R to the 8th minus U1. Okay, now I just factor out the S8, and then I'm left with R minus 1 here, and then I factor out the U1, and I'm left with R to the 8th minus 1 here, and then I'm going to isolate S to the 8th on this side, so I divide both sides by R minus 1. I get R to the 8th minus 1 divided by R minus 1 times U1. And now the only thing left to do is, now that we did this for a geometric sequence which is 8 wide and 9 wide, but if we just change the 8 to the n, so it's like basically we're saying, okay, what is the area of an 8 wide geometric sequence where the common ratio is 2, and we found out it's this, Well, we're going to make a general case out of that, and the 8 we're just going to change to an n. So all the 8s we change to an n. So now we know that the s sub n is actually equal to r to the nth power minus 1 times u1 divided by r minus 1, and this is the general formula for the sum. So this isn't a proof or anything, but it gives you an idea graphically why we're able to make such a small and simple equation to figure out the area of these, things that kind of just look like curves. The way we do that is just because when you multiply the common ratio times one of these sequences, it turns into a shifted version of itself. Okay, and so because of that, you can cover it in two different ways, and when you cover it in two different ways, you can set up an equality which eliminates a lot of extra variables. So now you can kind of see whenever you have a geometric sequence drawn out graphically, you can kind of see why it can be summed with this simple equation.